Okay, so we've identified the triangulation of lines, which is the 188, the 7th arc, and the fuel range plus 2, which comes down to this point here. So what do we do from this point onwards? Well, first thing is that we got this from 2 minutes after the fuel ran out. Fuel, 1 minute for the APU, 1 minute for the SDU, satellite data unit, to fire up. So we're 2 minutes into descent when we get to the 7th arc. That means that the aircraft has got about 120 nautical miles remaining capability of gliding. So we could draw a circle from this point of 120 nautical miles. This is 120 nautical miles. The aircraft must be inside this circle. So it must be north of this line here. It must be north of that. It cannot go any further than that. Okay, the next thing is what I call my minimum altitude calculation at the 7th arc, and this is how it works. It's a little bit complicated, but I'm going to try and work out a minimum altitude at the 7th arc. So in order to do that, what I've been doing is I've been looking at the minimum distance, the perpendicular distance as it were, to go between the 6th and the 7th arc. It's not very long, as it's only 8 minutes 31 seconds. And so we've got a little window on what's happening, or at least that's the way I looked at it. 8 minutes 31, to get from 6 to 7, even if you go the shortest possible distance, perpendicular, it has to be doing 387 knots. That's absolute minimum speed. All other speeds, all other tracks are longer. So the absolute minimum speed to get across from 6 to 7 is 387 knots. Now this aircraft, like every other aircraft, goes much faster, goes faster at altitude than it does at low level. So at sea level, we put this sea level here, and this is 30,000 feet, let's say. This is altitude here, altitude. At sea level, the aircraft can only do 330 knots, and at altitude 30,000 feet it can do Mach decimal 86, we'll call it, and so it's a sort of sliding scale between there. As you descend you get slower, so if we're going to be doing 387 knots average speed across from 6 to 7, we cannot be at sea level. It's impossible. It doesn't do 330 knots or at sea level for that time. I mean, it can only do 337 knots at sea level for that time. It must be higher. So if we assume that the aircraft is in descent, we can look at a typical descent. We know it's descending for 2 minutes, may have been longer, so let's assume a descent of 10,000 feet during the 8.5 minutes. 10,000 feet. Okay. So what we need to do now is say, where can we find a window which have an average speed of 387 and 10,000 feet? So we've got to pick it off here, and what actually happens is that you go across here and you find that at 19,000 feet starting to 9,000 feet, there's the 10,000 feet, you produce two speeds which are 359 at that altitude, and the one here is 431. Now the average of those, we've got 395. 395 knots. Well, that's a little bit more than 387. That's because we've got a headwind, so put in a headwind of 8 knots. That makes 395 the correct amount. So the aircraft is minimum altitude. In order to get across this, the minimum it can be is 9,000 feet and 359 knots. Now 9,000 feet times by 3 is 27. That is the number of nautical miles that the aircraft has to run from 9,000. It also has to slow down from 359 knots. That's another 15 nautical miles equals 42 nautical miles. So the aircraft has 42 nautical miles to run, minimum, if all the ducks are in a row, which we thought, from the 7th arc before it gets to sea level. It can be travelling perpendicular or maybe even down the 188. So if we drew 42 miles down the 188, here's 42 miles down the 188, that produces a point which is perpendicular distance from the 7th arc of 32 nautical miles. So we can draw a line here which is the minimum distance it must travel if it's still doing a normal flight. If it's spiraling out of control, obviously it'll just end up here, but we've looked there and it's not there. So if it's doing normal flight, then it actually has a minimum, absolute minimum of 32 nautical miles to go before it hits the sea surface. So it must be south of this new line that we've drawn at 32 nautical miles. It must be south of this line, it must be north of this line, and it may be on this 188 line. So we end up with a small triangle here which satisfies all three, as does both sides of this 188. It can be either side of 188. So in actual fact you'd want to extend this slightly this way. So this triangle that we end up with is this large, 7,000 square kilometers, which is an extraordinarily small amount in the greater scheme of things. That's going to require another 6% of what we've searched already, thereabouts, 6%. This has been just drawn by doing the maths, and so I did that on Google Earth, of course, and having done it on Google Earth, I pumped it all in, drew the lines, and we ended up with this. So here is the actual triangle, the green triangle here. It is bounded by a green line to the north. That is the 32 miles from the 7th arc, so it must be south of that. It's got a curved blue line running along the bottom there, which it must be north of that. That's the glide range line. And then it's also got the red line coming down the middle there, which is the 188. And as you can see, it self draws a triangle, and that triangle mysteriously has a big black line running through it. And that big black line runs through from the top to the bottom, runs through all the way here, out the bottom here, and that is the Goldfinch or Halefinch fracture zone. That is a bit of a coincidence, I would say. After 2,700 miles of nautical miles of flying south, we've ended up with a triangle that was drawn only by maths, and it has a large trench running right through it. This needs to be searched.